Okay, all right. So here's where we were last time. So we were talking about curls and Stokes' theorem and related facts. And one of the ideas that we started talking about was surface independence. And again, it's just completely analogous to the idea of path independence, and I'm going to show you a point of view on that in a few minutes that will underscore how extremely similar it is. What we had not quite talked about was this, what I call local test. And let me just remind you, we've already talked about these three statements. Now, we also talked about three analogous statements for path independence for your consideration, right? So, being a curl shows that a vector field is surface independent, and likewise, also, and much harder to prove, by the way, and well beyond this course, it goes the other way too. All surface independent fields are also curls. And again, let me just remind you, I'm assuming all the regularity that we could possibly want, and everything's different when those regularities are not there. And of course, there's this other point of view on surface independence, that all closed fluxes are zero. Okay, now, we further previously discussed that if every triple integral of a function is zero, well, the function has to be zero. So these two are connected by way of Gauss's divergence theorem, which says that all closed fluxes can be viewed as triple integrals of divergence. So the layout on the page, again, totally analogous to a similar argument that we made about path independence, aka gradients. And punchline being that we have our local test. If you want to know if your vector field is a curl, more often, if you want to know if your vector field is surface independent, here's the test. The test is compute the divergence, see if you get zero. If it's zero, vector field is surface independent. If it's not, then it's not. Okay, so here's how we can make use of that. And this is a powerful application. Here's the question. We want to compute a flux, right? And everything necessary is given. There's the vector field. There's the surface. How would I compute this flux? Well, notice nowhere in the question does it say anything about surface independence. Right? No suggestion that we should even entertain that. So what I'm going to do is I'm going to use the theorem that we just got through proving. Notice I compute the divergence of the vector field. I get zero. Easy partial derivatives to look at. Right? And because the divergence is zero, that means that yes, our vector field is surface independent, and that is a big conclusion to know that our vector field is surface independent. It means I can throw away my surface, replace it with any other surface, as long as it has the same boundary curve. Okay, so let's think about our surface for a minute here. We are looking at part of this elliptical paraboloid. Elliptical paraboloids are kind of like that. Right. Specifically, I'm only interested in the portion where z is positive. So I cut it here at the xy plane, as it were. My actual surface is just the part that's above there. So it's not the entire paraboloid. It's just that remaining green portion of the paraboloid right there. Everybody with me so far? I emphasize, got to be really careful with this. Here's a very common mistake students will make. Students will look very regularly at this picture and say, oh, well, I've drawn this as an indication of where the bottom is. This is where it's been cut. But that kind of makes it look like you're including this as part of S, as if S is this whole thing, both the sort of elliptical paraboloid top portion and this bottom face. Very importantly, it is not. Right? So notice, very importantly to how this is phrased, S is part of this paraboloid. Period. Right? It's part of the paraboloid. Every point on S is part of the paraboloid. Very importantly, these points here are not part of the paraboloid. Right? Does everybody see that? So this is a really dangerous little landmine you can step on by accident and inadvertently, just because of the ambiguities from how we draw things, one can accidentally confuse oneself and think that this bottom portion is included. Very importantly, it's not. Okay. All right, with that established, where is the boundary of my surface? And let me put these little kind of stripes back in there. Where is the boundary of this surface? The boundary, well, it's going to be all of that business right there. How we doing? Is everybody happy? Okay. All right, and now I feel like this is in the way, so I'm going to get rid of that. Okay, so now we just agreed on surface independence. That means I don't actually need this surface at all. In fact, the only reason I needed to understand this S surface was so that I could see what its boundary is. Because I've got surface independence, that means I can just throw away the surface, with the promise to replace it with any other surface I feel like that has this same boundary. And you might be able to see this coming. I have a pretty strong preference for this nice flat S2 surface there in blue. Much nicer surface with the same boundary. Everybody happy? And this blue surface, great in a lot of ways. For one thing, the normal vector is straight up or down. Perfectly obvious just from, it's part of the XY plane, so that's an easy alternative surface to choose. And we have to worry about orientations, but let me just show you how nice it is that we have this new surface. With this new surface in place, there's our new surface. We got rid of our old surface. With that new surface in place, and I'm going to come back and talk about orientations, but our normal vector having a bunch of zeros in it makes this dot product really great. Right, a lot of the vector field just gets multiplied by 0. We'll love it when that happens. All sorts of inconvenience gets thrown away. And in total, then the dot product is let's see how I'll do this in orange. This dot product ends up being just minus xy, and this is now a scalar surface integral. It's a scalar surface integral on a symmetric region. This integrand is odd, as it turns out, in reflection over that line, and this integral is equal to 0 by symmetry. So, a lot of effort of parametrizing the surface, taking the partials, crossing them to get the capital N vector, worrying about the orientation, blah, blah, blah. It gone, poof, doesn't matter. We already know the integral is 0. Everybody see how awesome that was? That's all because we can make the surface independence argument. Okay, so I think this is a lovely example. And let's move along now. So, y'all will recall this, what I like to call a strategic diagram for 2 dimensions. I'm not going to spend much time talking about this because we already have. Just want to remind you that this is there. And here in Chapter 7, of course, we've been spending a bunch of time talking about 3-dimensional vector calculus, and now that we've got all of our tools discussed, we're ready to talk about the 3-dimensional diagram. And here is a version of it. Let me just remind you where this came from. Just like the 2-dimensional version, this is what you get when you take some very sophisticated constructions, well beyond Math 219, chain complexes and cochain complexes and various formalities that, again, we're not going to talk about. If you boil it down and get rid of all the abstraction and rigor and complications and sophistications and just leave okay, well, yeah, but how does this apply just in 3 dimensions? Rubber meets the road for what we're going to need in Math 219. This is what's left over. And so this is ultimately a very natural, very powerful little organizational tool. And this is, again, representative of some very sophisticated, very powerful ideas. And so we're going to get to benefit from the power without having to pay the price of the sophistication. So again, I'm a big fan. You'll recognize our fundamental theorem of line integrals. previously discussed. Our Gauss's divergence theorem, previously discussed. Stokes's curl theorem. You'll recognize that we are composing gradient followed by curl, as we've previously seen, is exact. And we're also composing curl followed by divergence, which we have also previously seen is exact. So let me further point out. The fundamental theorem of line integrals can be thought of as saying that if you compute a gradient of a function and you take the boundary boundary of a curve, and if you compute on both sides, then your results are equal. That's a point of view. That's kind of how the diagram, that's how the fundamental theorem of line integrals looks on our diagram. That is the exact same diagrammatic representation as Gauss's divergence theorem, which is exactly the same as the diagrammatic representation of Stokes's curl theorem. They look the same on the diagram. Okay. By the way, reminder, this diagram right here is morally the same diagram. You'll notice it's still gradient followed by curl followed by divergence. We're looking at three-dimensional regions whose boundaries are two-dimensional surfaces, whose boundaries are one-dimensional curves, whose boundaries are zero-dimensional points. And all of the same theorems in all the same places. This is morally the same diagram. It's just kind of stretched out and a little bit more spacious and a little bit more sort of room to move. Nothing particularly different. I do kind of like working on this page a little better, though, because it is more sort of spaced out, and like I say, it's just a little bit easier to sort of work on. So I'm going to, from here out, I'm going to use this diagram. Y'all will do have access to a copy of this. This is called diagram.pdf. It's in the resources section of our Section Sakai site. So download at your convenience. I think you'll find it handy little reference tool. Okay, so we've talked about how the theorems all look the same. All right, Stokes's curl theorem, Gauss's divergence theorem, fundamental theorem of line integrals all look the same. Okay, I also want to remind y'all how path independence looks on this diagram, or what I like to call the special vector fields here. Special vector fields when you're talking about vector line integrals. Special because of several different properties. One is these special vector fields are gradients of actual functions, aka they have antigradients. And that's a nice property of these special vector fields. Here's another nice property. Curl is always zero, aka they're irrotational. Keep in mind, curl describes the rotational aspect of the fluid. So if there is zero rotational aspect in there, you might want to call it non-rotational, but I think the word is irrotational. English is weird. I also like to represent path independence bluntly, sort of literally on the diagram by, well, if you have two curves with the same boundary points, they will give you the same value of the line interval. Right? This is the special property of path-independent vector fields. So again, we're talking about all the same vector fields. The same vector fields in purple. They're gradients, curl is zero, and they're path-independent. Three separate properties of exactly the same vector fields. Again, regularity assumed, that we don't want to wade into regularity problems. Everything's different. Okay. Now, don't forget, when you have a gradient, that means that there is an anti-gradient for that vector field. That means that the fundamental theorem of line integrals is on the table. You could use the fundamental theorem of line integrals to compute that line integral. That's nice. In fact, let me go ahead and block the whole thing here. Furthermore, don't forget that the way we can see why it is that we have an exactness here is by making an argument, the key tool of which was Stokes's curl theorem. Right, and that was within the last, this week, as I recall. Okay. All right, so this is a bunch of information about these special vector fields, aka path-independent vector fields. And here's why I like to represent this on the diagram. I think there's a huge payoff as follows. Here it comes. All of this compact representation of path independence. Slide it over. Perfectly analogous to this compact representation of surface independence. It's the same diagram chase. It's all the same ideas, just shifted over by one. So let me talk you through this. Vector fields, these special vector fields that are curls, have divergence equal to 0 and are surface independent. Namely, if you have two surfaces with the same boundary curve, then you get the same flux. When there is an anti-curl, that's what tells you that Stokes's curl theorem is on the table and applies. And you could, if you can find that anti-curl, you can use Stokes's curl theorem. And the argument that shows us why these connect is an argument that uses Gauss's divergence theorem. In fact, that's what we just talked about seconds ago. The thing that connected divergence being 0 to being a curl, aka being surface independent, that connection was made by Gauss's divergence theorem. Right? So it's a wonderfully elegant fact that everything that you can say here about surface independence is analogous to things that we already knew about path independence. Why is this useful to you? Well, if you're having trouble, for example, making sense out of, why is Gauss's divergence theorem, what does Gauss's divergence theorem have to do with surface independence? Well, take that question, translate it over, and you can see that the answer is that, it's in the same way that Stokes's theorem was useful for path independence. Right? So your understanding that you may already have of certain ideas will, by analogy, allow you to extend that understanding to this other sort of analogous context. I think that's really useful. Okay. Here's another way of thinking about it. So we've got, again, kind of 5 different theorems here. We have, fundamental theorem of line integrals, Stokes's curl theorem, blah, blah, blah. So three theorems here on the R3 diagram, 2 theorems here in the R2 diagram. Let's not forget, by the way, there's also the fundamental theorem of calculus, which is the one theorem on a what you might call a one-dimensional diagram that I won't draw because we don't really need to. But there are arguably those 6 different versions of this one theorem. Case could be made, you really don't even need to memorize those 6 theorems. If you know the diagram, then you only need to know this one pattern. Right? If you have trouble remembering, for example, how does Stokes's curl theorem work? What was Stokes's curl theorem again? Well, you can just fill in the blank from the pattern that, apparently if I have a vector field and I compute its curl, and then if I look at a surface's boundary curve, that original vector field over the boundary curve compute a line integral, the curl over the original surface compute the flux, and you get the same thing on both sides. The diagram tells you the theorem. All you got to know is the pattern. I think that's pretty cool. Okay. So all of this, of course, assumes that you have the diagram to work with, and I know there's a lot on the page, and it seems like it'd be a lot to, I don't know, are you going to memorize that diagram? And actually, yes, I strongly encourage you to memorize this diagram. In fact, I'll bet you may have accidentally already memorized most of it. Because, in fact, there's really only a couple things to know. You do need to know the order that these operators go in. That's true. That you need to memorize. Make sure to memorize that order. Grad, then curl, then div. Yeah, question?
So, will this not be provided?
Correct. It's not going to be provided on the exam. That's right. This is something to remember. Yeah, absolutely. But so again, look how easy it is to remember. Once you know the order that these three things go, well, I mean, it's kind of a freebie what these boundaries do, right? If you have a three-dimensional region, the boundary is going to be a two-dimensional surface. Well, of course it is. That's just geometric intuition. And if you have a two-dimensional surface, well, the boundary is going to be a one-dimensional curve. That's just, well, of course it is. What else would it be? So that you don't even have to memorize. This is just a sort of geometric understanding thing. How are we going to evaluate a function on a three-dimensional region? Triple integral is the only thing we've ever talked about. Right? How would we evaluate it? What sort of evaluation uses a vector field on a surface? Well, flux. It's the only thing we've ever talked about that has a vector field as the integrand and computed over a surface, et cetera, et cetera. Yes, you have to memorize the pattern. Again, that's not that much, right? So again, you may have inadvertently already memorized this diagram. So I think a really healthy exercise is take a clean sheet of paper at some point and don't look at the actual diagram here. Just take a clean sheet of paper and see if you can reproduce it. And if you can, super. And if you can't, then okay, well make sure to look at what it is that you couldn't fill in the blanks on and think through and make sure to understand that part. But then try it again. You can probably do it. Okay, for whatever it's worth, when I'm doing vector calculus questions myself, this is always in my mind. This is how I organize all of these thoughts in my head. It's all based on this diagram. Okay, I want to talk now about how to use this. We're going to do some examples. Here's a bunch of, well, let me get down to it. Here we go. Bunch of examples. And the big idea is let the diagram be your guide. Identify where you are, given the question that you've been asked, where you are on which diagram. And it basically tells you the players in the game, what to do, and gives you ideas for which theorems you therefore might apply and which theorems you won't. Okay, so let's look at this example here. Example 1. First of all, notice our parametric curve, 3 coordinates. We're in 3 dimensions here. Okay, and furthermore, we're computing a line integral in 3 dimensions. So, here we are, 3 dimensions. We're interested in a line integral. These are therefore our 2 theorems that we might be able to use. Everything we're going to need should be in this portion of the diagram, and right away we know that Green's operator, not going to come up. Right? Green's theorem. No, that's just not relevant. It's in the wrong dimension. Furthermore, divergence should not come up. There's no reason to talk about divergence. If you've been asked for a vector line integral, right, this is just not going to be relevant. Does everybody see what I'm talking about there? It's just not connected to line integrals in any way. There's no triple integrals in this question. Gauss doesn't come up in this question. Yeah.
Wait, why do you think Green's is not relevant?
Because that's a 2-dimensional theorem, and the question we've been asked here is a 3-dimensional question by virtue of the curve having 3 coordinates, so we're in 3 space.
Yeah.
Yep. All right. So on a question like this, now I want you all to keep in mind, on the final exam, I will not be the grader. Right? On the final exam, it's done in a different way. It's a committee grading process. The graders are going to be like all graders are going to be reading everything that you write and trying to get inside of your heads. Try to figure out, what does this student really understand and what does this student not understand, right? So there's a certain amount of kind of speculation on that. And if on your paper you have a bunch of stuff that's completely irrelevant that you haven't crossed out, right? You can cross out anything you want. If you cross it out, you're not responsible for it. It's like it was never there. It's complete disavowal, right? If you've got triple integral on the page, it makes it look like you don't know what's going on, right? It's a bad look, right? It has no chance of being relevant. Makes you look confused. So, if only to keep the graders in the right mindset of giving you the benefit of the doubt, which we want, right? I want the graders to give you all the benefit of the doubt. For a line integral question, I don't want to see any of that stuff, right? It's a bad luck. Bad luck. Okay. All right. So that said, what do we do again if we are interested in computing a line integral? Well, let's see here. The next thing we're going to do, it says compute the appropriate operator, compute the appropriate boundary, and then infer from that. So what does the diagram tell me to do? Well, I'm interested in computing a line integral. That means they've given me a vector field. What does the diagram tell me? Well, the diagram's telling me right here, compute the curl of that vector field. So go ahead, compute that curl. It's also telling you, whatever curve you're looking at, think about the boundary points, if any, of that curve. So let's just do what the diagram tells us. Here we go. Let's see. First, we're going to take the curl of this vector field. And that's various partials to compute. And let's see here. You'd think I'd remember from having done this twice already today, but let's see here. 0, 2x minus 2x, also 0. Okay, it's coming back to me. 2y minus 2y, also 0. Okay, so the curl is 0. It's the 0 vector. So, back to the diagram. I computed my curl. I got 0. We know that means that there is an antigradient. And that means that the fundamental theorem of line integrals is on the table. That could work. That's an option. There is an antigradient that I can use, so we have a way forward on this question. Everybody with me? Notice all I did is just do what the diagram told me to do. I didn't even have to decide. Just following the diagram's instructions. Okay. All right, next. For the given curve, I need to think about the boundary points, apparently. Okay, as instructed then. All right, well, let's see. We'll plug in 0 into there, and x of 0 is, okay, let's see, it's 0, 1, 1. And then let's see, now I will plug in 1 into there, and that gives me x of 1 is negative 1, 1 e squared. Okay, now what does this tell me? Well, sadly, what this is telling me is that this curve here, I'm deciding on colors. This, whoops, wrong. This curve right here, kind of like that, right? It starts at one point, it ends at a different point. And, well, that means it's not a closed curve. That means it couldn't possibly be a boundary. Right? Does that make sense? Okay. God, I'm sorry. I don't know where that's coming from. So, okay. So we've got an open curve. By the way, here's a nice way to think about boundaries and what that tells you. Every curve either has a boundary or is a boundary. I think that rolls off the tongue really nicely, and it's a nice sort of memory tool. This one has a boundary. Therefore, it can't be a boundary. Right? Whereas, by contrast, this curve here is a boundary, but it does not have a boundary. That makes sense to everybody? Again, I think it rolls off the tongue nicely. Okay, so back to the diagram. We've got, we took the boundary. The boundary was not 0, therefore there is no anti-boundary surface. That means Stokes' theorem is right out. There's no surface over which to even talk about Stokes' curl theorem. So our way forward is clear. Yeah.
So in the question when it says compute the with the boundary C f dot dx, so we're going about it with this graph by kind of starting with the curl because that's the way the arrow's going. But we know from the beginning what we need to compute.
Oh well, the question asked us to compute vector line integral.
So we can either do that from computing the curl and going backwards, or from the gradient.
Yeah. So right off the bat, if before we did any of this analysis, just knowing only that we're trying to compute a vector line integral, well, who knows? Maybe this might work. Maybe that might work. We hadn't really decided yet. Right, but what we see is that no, you can't use. There's no surface in play. So Stokes' theorem does not apply. Right. That's not an option. But the fundamental theorem of line integrals does. Yes.
Oh, when you say boundary, you mean closed boundary, right? Like there's no closed boundary between the two points, but there is.
I don't know what you mean.
Like there's a line, but there's no closed boundary.
You talking about this curve here?
Yeah.
So this curve has the boundary of a curve means the starting point and the ending point.
Yeah, but it's not closed, so we can't use so that means we just can't use Stokes, right?
This I don't understand your question. So this curve has a boundary, full stop.
Or you said like
there's no such thing as a closed, but closed means it doesn't have a boundary. You know what I mean? It means it is a boundary, but that's not the same as having a boundary. I'm not sure. Maybe this is just a lingo issue.
I guess I'm a bit confused about the wording.
Yeah, okay. So when you say a curve has a boundary, that means that if you talk about the boundary of the curve, then there's something there. And boundary of a curve refers to the starting point and the ending point. Right? So now if, on the other hand, if we were looking at a curve like this curve does not have a boundary. Does that make sense?
Yeah.
Because it kind of, you could say that it both starts and ends at that point, but I also could say that it both starts and ends at that point, whatever. It's kind of the same curve. But there really is it never stops. It never starts at all. On the other hand, this curve is a boundary in the sense that it is the boundary of this.
Oh, so you're saying that the start and the end are the same?
Yeah.
So it's not really like
a... So yeah, in practice, there really isn't anything that you could point to and say that is the boundary. Right, yeah, exactly. Is that satisfying?
So there's no bound points?
Yeah, right. Okay, so, we know what to do with this question now. Our analysis on the diagram tells us that don't even look at Stokes. Well, correction. We tried Stokes, it didn't work. Right, it doesn't fit. But fundamental theorem of line integrals works just fine, and go ahead. So that's how I do this question. And I'm going to leave the details. We've already done a bunch of these before, so I'm not going to work out the details on this. Okay, let's look at the next one. Whoa, wrong. Okay, here we go. Next one. Different vector field, different curve. But again, notice 3 coordinates. That means we're in 3 space, computing a line integral. So again, our context is the same. Let me clean up this mess. We're again there. That means we're only looking here. It remains that we're going to steer clear of any of that stuff. We're not going to talk about three-dimensional regions or triple integrals or divergence or Gauss. None of that has any chance at all of being relevant. Keep that off your page. What we're going to be doing is taking, again, our vector field, compute the curl, our curve, compute the boundary, think about the boundary anyway, and draw conclusions from that. So here we go. Let's compute the curl. And again, in the interest of time, I'm just going to give this one right out. That's easy partial derivatives to compute. Actually, very easy partial derivatives to compute. Make sure that you're comfortable with that this works out to 0, 0, 0. And what does that tell us? Back to the diagram, we computed the curl. We got 0. That means there is an anti-gradient. So fundamental theorem is on the table. We've got a reasonable way forward. Okay, is everybody with me? All right, now let's think about the boundary. Okay, so I've got to look. Oh man. Fine. Okay, so we'll plug in t equals 0, and x of 0 is 0, comma 1, comma 1, and then I plug in t equals 1, and x of 1 is 0, 1, and 1. How about that? So our 2 points here are the same. This curve starts and ends at the same point. It starts, let's say, there. The curve goes around and does all sorts of weird stuff, and then it ends right back where it started. Effectively, then, this curve has no boundary. It just kind of keeps going. It's like a racetrack that, you can just, when you get to the stop, you could just keep going again. Does that make sense? Okay, so the boundary is 0. Let's see here, color choices. That's 0. That means that there is an anti-boundary surface. That means Stokes' curl theorem. Also, excuse me, also on the table. And now, what is this anti-boundary surface? What is this thing here? This would be the surface that I would need to use if I were going to use Stokes' theorem. And how to find that? That's a little weird, right? If you look at that curve is all sorts of. That's a weird curve. So exactly how we're going to find that surface, not clear. Yes.
So if we have a figure 8, are we just saying that the circulation cancels each other out, basically?
If we have a what?
Like a figure 8.
Okay. So you're on a hypothetical?
Yeah, hypothetical.
Okay. So hang on a second then. So you want to talk about a figure 8?
And if the start and end is the same, then we're just saying the circulation, like intuitively, is canceling each other out.
No comment on the circulation here. All I'm saying for a shape like this is that independent of it crossing itself in the middle, this curve starts and ends at the same point.
Well, if it was a conservative vector field.
If it's conservative vector field, then that's right. But that's right. But the key point there is that it's conservative. The fact that it's a figure 8 doesn't really matter.
Yeah.
Does that make sense?
Yeah.
Okay. Cool. All right. Okay, so we have 2 candidates here, right? We could use either the fundamental theorem or Stokes' curl theorem. Now, I have bad news for both. Unfortunately, we've already talked about the bad news for trying to use Stokes' theorem, and that is that I don't know how to figure out what that surface is. That's weird. That's the bad news. Here's more bad news. If I were to find the anti-gradient, I'd be taking anti-partials of these functions, which are all at least a little inconvenient to deal with. I'd have to do 2 integration by partses just to find the x anti-partial. And worst, we don't even know how to find an anti-partial of that. So the function f is going to be really hard to find. The surface S is going to be really hard to find. This is bad news for both of these examples. Now here's the good news. It actually works out really nicely, keeping in mind that we're interested in this line integral right here. This line integral right here. If I were to use the fundamental theorem, and it's f of x of 1 minus f of x of 0, to be fair, I don't yet know what that function is, but I do know that these are the... Oh, come on, stylus. I do know that these are the same point. So I'm computing at the same point, so it doesn't really matter what the function is. Right? So yeah, it's going to be hard to find f, but I don't need to because I'm looking at f of 1 point minus the same f at the same point. So this difference is clearly 0. Lucky break. We got lucky. Everybody all right?
We can also say the same because curl is 0 too.
That's exactly right. So let me fill in those blanks. Yeah, exactly what you said. Using Stokes's curl theorem, I would get flux over this mystery surface of the curl dot ds, which looks bad right up until you recall, just as you pointed out, that the curl is 0 anyway, so we don't need to know the surface. We're computing the flux of 0 through it. So not a problem. So take your preference. You can compute this either way, whichever one you like better. Everybody good? Okay. All right, third example. By the way, just real quick, I'm looking at the clock, realizing there's no way in the world we're going to finish this today. So first of all of this is supplemental. So, I hope we get through as much as we reasonably can. But it's all gravy at this point. Secondly, I do have recordings that I'm going to make available to y'all that that go through all 6 of these examples. So if you want to see more discussion of the examples that we're not going to have time for, you can just watch those recordings. But again, it's all supplemental. Think of this as studying for the exam 3 and the final. It's not really new material. None of this is new ideas. Okay. All right. So again, 3D line integral, same context in the diagram. Let's clean up the picture. Let's see here. Computing curl. Oh, whoops. And I happen to recall -1, -1, -1. It's not 0. Okay, well, bummer. We computed curl, not 0, no antigradient, no possible use of the fundamental theorem. Oh well. Too bad. What can I say about my surface? Let's look at our curve. Our curve. Well, I have a cylinder. And I have a plane. And the curve we're interested in is that intersection of the two. So it's something kind of like that. Everybody good? Now, what did I need to know about the curve? Apparently I needed to know about the curve. Does it have boundary points? And no, it has no boundary points. That means that there is an anti-boundary surface. That means Stokes's curl theorem is an option. And you can actually see that in the picture. You can see, you can see the surface in question. I keep hitting the wrong button. There we go. There's the surface. All right, notice that surface is just part of that plane that cut through the cylinder in the first place. Everybody with me? So Stokes's theorem's on the table. That's an option. Now I'm going to point out on this one that there is a third option, which actually might realistically be the best way to go, and that is just parameterize the curve. This curve is actually easy to parameterize. I'm going to parameterize this curve for you right here. So keep in mind, this is the curve we're talking about. And notice its projection into the XY plane is just a circle. We know how to parameterize circles. So if I want to write down XYZ for this curve, just from the fact that x and y are going around in a circle, I'm just going to say cosine t sine t. Everybody follow that part? Now there's the question of z. Where am I going to get z from? Well, don't forget this entire curve is also on the plane, which has this equation in which I can straight up solve for z. Z is apparently minus x minus y. So, okay, that means I get minus cosine t minus sine t. So, your options on this question. You can use Stokes' theorem to do a flux of this curl through this surface, which wouldn't be that bad, I suppose. Or you can just straight up compute the line integral by pulling back through this parameterization. Look at our vector field. Our vector field's not scary. Honestly, between these two options, I think I'd probably use the parameterization. If it was me. Now, what I'm going to recommend for y'all to do is to try it both ways. I think it's a healthy exercise both ways. Compute the flux of the curl through this surface, which, of course, don't forget to notice this surface is a graph. So you can use the graph parameterization to parameterize that surface and compute that flux of the curl. And then also, just compute the line integral directly with this parameterization. So you're going to get the same answer both ways, and both of them are healthy exercises. So give that a try. Now that said, example 4 works out a little differently. Example 4, very, very similar. Same vector field, still a cylinder intersecting with a plane. The only thing is it's a different plane. Still computing a line integral. Everything's the same except for a key detail. And let me draw the picture here. The key detail is, I'm getting ahead of myself. I can talk faster than I can draw, apparently. So let's see here. So we have our curve, we have our new surface. All this is very, very similar, but check this out. This plane is different. That means that my normal vector is different. And I can, to a large extent, I can read the normal vector straight off of that plane, right? Notice that my surface is part of this plane. So that means I know right off the bat. Now there's the issue of orientation that I'm going to get to later. But other than that, we're talking about 1, 0, -1. And then I've got to divide by the square root of 2 to make it a unit vector. But I know my unit normal's got to have to be pretty much that, asterisk, worry about orientation. So let's write down then Stokes' theorem, which we know applies. Stokes' theorem would say I'm doing a flux through my new surface of the curl, which we already computed, dot my normal vector, which I just got through talking about, is, possibly plus or minus. We'll deal with that later. But 1, 0, -1, factor of square root of 2. Here's what Stokes' theorem would say. And with our normal vector, with our normal vector known, and with curl also known, this dot product is just 0. You get lucky sometimes, right? You always have to have head on a swivel, always be on the lookout for this possible good fortune. But I don't need to know the plus or minus in here about the orientation, because either way, 1, 0, -1 dotted with -1, -1, -1 is 0. This integral is 0. Game over. And whether it's plus 0 or minus 0 doesn't really make any difference, does it? So sometimes you get lucky, and be on the lookout for this sort of thing. Okay, we're out of time, and again, there's 2 more examples here. I'm going to refer you to the videos that I'm going to, if you want to, again, this is all supplemental, right? But if you want to see an explanation of these last 2 examples, you can watch those videos that I'll send I'll send when I get back to my office. And hope you all find that useful, and have a good weekend. See you Monday, in which we will talk about chapter 4. All right, have a good one.